Hello, everyone. Good evening, good evening, good evening. How is everybody doing? I believe you're doing great. How are you guys? It's been a while. Please don't mind me. This is the first time recording a YouTube video, so I'm kind of nervous. All right. How's everybody doing? I believe you are great. Please, if you are hearing me, please indicate in the comment section that you're hearing me. I want to make sure that everybody watching this is actually hearing me. If you are watching this, please indicate in the comment section that you're hearing me. Yeah? It helps me know that people are actually listening, because this mic, I hope is working. I really hope it's working. All right, let's get into it. Classical physics. Now, lots of things. There are things I'm actually thinking about right now. Classical physics. A very important branch of physics. If you are a science student, actually you do not even have to be a science student. I believe that knowledge, the kind of knowledge that science affords the average person, is unprecedented. It helps in everything. It applies in everyday life. Physics is applicable in our day-to-day lives. Physics is how we know the speedometer in your car, right? Physics rather is how we know the boiling point, the freezing point of pure water. Physics is how we know every single thing basically that we use or that we encounter, we come across on a daily basis, from tiny particles on Earth to the stars in the universe. Physics is the reason why we are aware, right? Physics is the reason why we are not in the medieval times. And it's not just that. If you look at the way humans progressed, if you look at the evolution of Homo sapiens, you see that we went from, a bunch of growing species who were scattered, suffering in search of food, to technological advancements in the universe, right? To some of the best things that we've been able to create, right? It's development did not just happen. Human development did not just happen in a vacuum. Yeah, we had a lot of resistance. We had a lot of things we had to overcome as a shared society and ensure progress no matter what. Now, there's a geopolitical reason for the development of humans, as well as a scientific reason. And for me, I think the scientific reason for our development is the most significant. Yeah, is the most significant. Now, talking about science, if you look at the progression of science, right, from ancient civilizations like Greek, like Germany, like the United States, places where we had ancient civilizations, places like China, right, places that afforded us an opportunity to know what we know now. If you look at the progression of our scientific discovery, you would see that, first of all, we began with assuming things, right? Because we did not have any way of measuring quantities. We did not have any way of, quantifying the we didn't have measuring systems to begin with. No, we didn't have any kind of measuring systems, right? So because we didn't have measuring systems, we relied on assumptions to push our points, right? We relied on things like faith, right? For those of us that are religious, you know that we relied, as ancient civilization, there was a time when the church, specifically the Catholic Church, I believe, ruled the world, right? They were the rulers of ancient Roman society, right? They ruled Rome, and they gave us a lot of philosophies then, right? And the scientific study that time of the globe, was referred to as natural philosophy, right? In ancient times, natural philosophy encompassed science, philosophy itself, and religion. Yeah, those are the three things that the term natural philosophy encompassed, right? In ancient times, natural philosophy. So when we say natural philosophy, it doesn't mean now what it used to mean then. It used to combine, science. It was used to combine science, philosophy itself, and religion, right? And that is a dangerous combination if you think about it, right? It's a dangerous combination. The reason it's a dangerous combination is because oftentimes they are at odds with each other, especially science and religion. But the people of old who didn't know better, right? Scientific and famous great scientists and philosophers like Aristotle, Plato, they had a lot of predictions in the universe, right? So during the 19th century, yeah, during the 19th century when we started having, that the 19th century was, for me, a century of enlightenment, because that was when we started having some of our biggest breakthroughs in science. That was when we started, scientists like Galileo. There's a guy called Galileo Galilei. He was the among the first scientists to help us put scientific concepts as sorry as broad and as disorganized most scientific concepts were at the time, because there was no way of measuring systems. Galileo, alongside some other scientists like Kepler and the likes, they put together, they made science make sense. Yeah, they made science make sense to the average person, right? They made science make sense. It was during that period of time that we had great scientists like Isaac Newton. Yeah, these scientists were not just scientists as at that time, because science was not a popular reality in the time. People just assumed things, but these people were able to sit down, observe the universe, make up mathematical concepts that defined the nature of the universe, right? These mathematical concepts is what enabled us to not just assume things anymore. We went from assumption to real hypothesis. Sorry, real hypothesis, right? We went from just thinking that things happen to actually calculating how things happen, how things work. Yeah, that was one of the few things that defined the 19th century. But among all, there were one of the things that the likes of Galileo was among the few physicists, right, who introduced the concept of classical physics, right? The concept of classical physics. Now, classical physics, I wrote down on the board. If you can see the board, please, if you can see the board, indicate that you can see the board. Classical physics, think of classical physics as old physics, right? Think of it as the physics before the modern physics. Right now, science or physics in general is divided into two. classical physics and modern physics. Yeah. And classical physics refers to the old kind of physics, and not just, it is old, but it is not irrelevant, right? We still use them, we still study them today, and the reason they are relevant is because they describe something called macroscopic macroscopic objects. Yeah. Macroscopic objects refer to, big objects. Like macro means big, right? So classical physics, the reason classical physics is still of importance now is because in a time when physics in general was not understood, any new explanation of how the universe worked was accepted, right? And classical physics was the branch of physics that explained the things that we use in everyday life, right? The things that we use in everyday life, right? Classical physics explained a lot of things. Now, just give me a second, right? It was classical physics that gave us an idea of why a stone falls to the ground, for instance. Yeah. Why a stone falls to the ground, why heavier objects and lighter objects fall at the same time. It was classical physics that gave us an explanation. Now, you remember when you were in school, right, and your physics teacher was trying to explain, I believe you must have come across a situation where they told you that between a heavier object and a light object, when you carry a heavier object and a light object, and maybe you stand in a tall building and you release the heavier and lighter object, the question then that they used to ask us was, which one will fall faster, right? Let's say you use a stone, right? Let's use a stone. Yeah. You use a stone and then you contrast the stone. You have a stone and something else, something lighter, maybe a paper, right? Let's use a paper, a stone and a paper, and they tell you, if you release a stone and a paper into the air, which one falls to the ground first? Of course, every one of us were like, oh, it is the stone, because the stone is heavier, right? That is the basic human assumption, that the stone will fall first before the paper falls, right? Now, the problem with that assumption is that the stone falling depends on the weight, right? Like how fast, okay, yeah, how fast an object falls depends on the weight of that object, right? But in classical physics, we were able to learn that the reason the stone will fall faster than the paper is because the paper itself that is falling slower, air resistance, right? Air resistance is a factor that slows the paper down relative to how fast the stone falls, right? So, but classical physics explain that in a vacuum, and by vacuum I mean assuming there is no air resistance, right? It is air resistance that makes a heavier object fall faster than a lighter object. But assuming there is no air resistance in play, the stone and the paper will fall at the same time. They will land on the ground at the same time, right? And we've tested it. There has been lots of experiments to test this, right? Where we've tested in lots of vacuum. I think one of the most popular experiments was when I think it was an astronaut that went to space, right? And space is there's zero air resistance in space. There's almost virtually no air in space, right? And I think there's zero gravity in space as well. So he dropped two objects, and the two objects fell at the same time. Yeah, that's exactly what happens when you put a stone side by side with a paper and there's no air resistance. When there's no air resistance, the stone and the paper falls at the same time. Yeah, that is the reason we're able to know that that truly the how fast an object falls depends on more than just the weight of the object, right? It depends on things like air resistance, right? It depends on things like gravity, right? Not necessarily gravity does not necessarily have a full or a huge effect, right? But it does have an effect, right? And it's not just the weight of the object that determines how fast the object falls. That is a knowledge we were able to acquire because of classical physics, right? Specifically because of the work of a scientist called Galileo Galilei. Yeah, Galileo Galilei. He was the one in the 19th century, the 1900s, that explained the laws of falling bodies, right? He explained something called the law of falling bodies. The law of falling bodies, right? Now, the law of falling bodies was a concept that Galileo introduced in physics that explained why a heavier object like the stone in the example we used earlier and a lighter object like the paper we used earlier can fall at the same pace when there's an absence of air resistance, right? And he carried out an experiment, right? He carried out an experiment in, well, we do not really have evidence that he actually did the experiment, right? But legend has it that he did an experiment in a tower. There's a place in Italy, right? Right now that place exists right now in Italy. It's called the Tower. It's called the Tower of Pisa. The Tower of Pisa, right? The reason it's called the leaning. Okay, I think it's called the Leaning Tower. Excuse me. It's called the Leaning Tower of Pisa. Right? You can Google it later, but it's called the Leaning Tower of Pisa. The reason it's called the Leaning Tower of Pisa is because it is a building, right? It's a tower. A tower is a tall building, right? It's a tall building that is tilted, right? The building is bent. It's not straight, right? It's tilted. So legend has it that Galileo did an experiment on that Tower of Pisa where he dropped a cannonball, right, a round ball from the top of the building, right? Because the building is tilted, it is an inclined plane, right? It is an inclined plane, and in an inclined plane, that was how he confirmed the experiment himself. A heavier object and a lighter object falls at the same time. Right? So the law of falling bodies, it was classical physics that made us understand the law of falling bodies. Now, Let's go back to the base. What is classical physics? Right? If you look at the board, if you can see, please, if you can see the board, tell me you can see the board. Right? I hope you can see the board clearly. I hope you can see the board clearly. Now look at the definition of classical physics on the board. Now it says classical physics is the branch of physics that describes the behavior of macroscopic objects. Now, underline macroscopic objects and physical system using theories developed primarily before the emergence of modern quantum physics and relativity. Right? Before the emergence of modern quantum physics and relativity, right? It describes the behavior of macroscopic objects, right? Why is the behavior of the description of the behavior of macroscopic objects important? Because bigger objects do not behave in the same way as tiny objects or smaller objects, right? So it requires a different kind of physics to explain the behavior of bigger objects, right? Bigger objects are like objects on that we use on a daily basis, right? Objects like a moving car, right? A car is a bigger object, right? Objects like a moving car, right? Objects like maybe a jet, a plane, right? Anything that is big or anything that is, that we use on a daily basis, right? So the central idea was that all macroscopic objects exhibit motion that obeys certain mathematical principles, right? There are certain mathematical principles that macroscopic objects. Remember, I told you macroscopic means big, right? Just like microscopic is referring to smaller objects. Now, macro means big, right? So macroscopic objects means big objects, large objects, right? Those objects are better explained. Macroscopic objects are better explained with classical physics, right? Classical physics is the introduction of a new kind of physics in the 1900s that explain the effect of bigger objects, the motion of bigger objects, the forces affecting bigger objects, the speed of bigger objects, right? And the nature of bigger objects, right? Basically, objects that we use on a daily basis, right? So now, what are the examples of classical physics, right? What does classical physics explain in the real sense of the word, right? Now, bear with me. right? A few things that classical physics explain is how a stone falls to the ground, one, how a car moves and accelerates, how the planets orbit the sun. We are able to know these things because classical physics, or how these things work, because classical physics explained it to us. Yeah, it explained it to us. Now, there are a few things. There are a few things in classical physics that you have to know, right? One of the things that classical physics, one of the concepts that classical physics introduced to us was something called classical mechanics. One of the things classical physics explained to us was classical mechanics. Now, mechanics or classical mechanics refer to it is the branch of physics that deals with the motion of bodies under the influence of gravity, or under the influence of force rather. The branch of physics that deals with motion under the influence of force. Let me write it. It is the branch of physics that deals with motion under the influence of forces. Now, those forces can be gravitational forces, right? Those forces can be, different forces in physics, right? Different forces in physics. They can be anything, right? Now, there are tons of there are tons of forces in physics that you have to know about, right? Or concepts in physics that you have to know about, right? We have to understand that, okay, we talked about how classical physics gave us classical mechanics, right? And we said that classical mechanics is the branch of physics that deals with motion under the influence of forces, right? What does that mean? What does that mean? Yeah? What does it mean? How does it apply to everyday life? Right? How does it apply to everyday life? Now, coming, I'm coming. Uh, there's something in physics called uh, Aristotelian view. Aristotelian view. So is this basic idea that for an object to move, a force has to act on it. So which means if I drop uh, if I drop an object in a table, for instance, the object will remain on that table until something moves the object. Now, this Aristotelian view was because the word Aristotelian came from a famous scientist called Aristotle, right? Aristotle. and he was the one that said he was the one that argued, right, during his time, that he argued about things like, heavier objects falling faster than lighter objects. He really believed that. Yeah, he really believed that if you place two objects of different weights, a higher weight and a lesser weight, that the one with the bigger weight, the heavier object, will fall faster than the lighter objects, right? He believes that. Now, the problem with that belief is everybody in his time actually accepted it because he was a very popular philosopher. He studied natural philosophy, right? So he was recognized as a scientific mind, right? He was recognized as a 19th century thinker, right? So when he argues that the heavier object falls faster than the lighter object, everybody believed him. There was no evidence to prove that there is actually a possible scenario where the heavier and the lighter object will fall at the same time. There was no such scenario, because Galileo, right, his view came later on after Aristotle, right? So while Aristotle was predicting that objects that are heavier will always fall faster than objects that are lighter, he did not give heed to a situation where there's zero air resistance, an ideal situation where there's no air resistance to the heavier object, right? So one of his beliefs was that the heavier objects must definitely, in all circumstances, he was so sure that in all circumstances, heavier objects must fall faster than lighter objects, right? He was so staunch on that belief that during his time, there was almost no opportunity for openness to something that would challenge that idea, right? Now, the Aristotelian view is based on two concepts, right? Just two concepts. The first concept is that he believed that objects move only when a force acts on them. That was the first thing Aristotle believed, right? The second thing Aristotle believed was that heavier objects fall faster. That heavier objects fall faster. Heavier objects fall faster. Now, let me make way so you can see what I'm writing on the board, right? He believed with everything within him that objects can only move. His first belief, or his first view, was that objects can only move when a force acts on them, right? Now, that was true until the early 20th century, where we had great thinkers, great thinkers like Isaac Newton, right? No, Isaac Newton was in the 19th century, yeah, until Isaac Newton came. Now, remember, Newton developed three laws in physics, right? He developed three laws. Remember Newton's first law, right? In case you don't know, Newton's first law proposed that an object will remain at rest unless acted upon by an external force. An object will remain at rest, or an object will keep moving unless acted upon by an external force, right? during the classical physics era, right? In classical physics, we had, remember in classical physics, what I said earlier, we had Galileo, right? The few people who we had during the classical physics time was Galileo. The second person we had was Isaac Newton. We had another guy called Kepler, right? We're not going to go into Kepler now, but Kepler proposed laws that educated us on how, how the planets move around the sun, right? How the planets are in orbits, right? We'll treat that another time. But Kepler did justice to that. But the major people I want to highlight was Galileo and Newton, right? Galileo opposed the second Aristotelian view that says that heavier objects fall faster by introducing something called the law of falling bodies, right? Where he said that the only reason a heavier body will fall faster than a lighter body is because of the presence of air resistance, not necessarily gravity, right? But in a vacuum where there's no air resistance, assuming there's no air resistance, the heavier objects and the lighter objects will fall faster. It was Galileo that proposed that, right? And that cancelled out the second view that Aristotle was heralding in his generation, right? It cancels out that view, right? Because Aristotle only believed that the heavier object must fall faster. That's false, and Galileo disproved it. Right. Now, Galileo's first view, which was that objects only move when a force acts on them, was also opposed, but it was not opposed by Galileo himself, it was opposed by Newton. Right. Now, while Newton, one of his laws, he proposed that it's force is only required to start or to make an object that is stationary move, and to stop an object that is already moving. That is his law, that is his proposal, that force can only make an object that is not moving to move, or make an object that is already moving to stop. But an object's motion does not depend on only when a force affects it. So in other words, when an object is in one place, you require force to move it, but force is not the only thing that is required to move an object, right? Force is not the only thing that is required to act on the object to keep moving, right? There are other factors in which Newton proposed. There are other factors, there are other kinds, of forces that are acting on a particular system. It is not always automatic. Yeah, it is not just force. There are other factors, right? So by saying that it is true that force is responsible for the movement of objects, but it is not exclusive that force is the only thing responsible. Right? That was one of the proofs of Newton. Right? One of the proofs of Newton. Now, the aim of this class is to introduce you to, or to take you back to a world that introduced the kind of physics that we know today. The kind of physics that we know today. The kind of physics that we knew today is only possible because of great minds like great minds like the likes of Galileo and the likes of Newton, right? Newton and Galileo expanded on the ideas of Aristotle. The ideas of Aristotle were fixed. Right? Newton expanded on it. Right? But even though Newton and Galileo expanded on it and gave us what we know in classical physics, their hypothesis still had a limitation. It was limited by a lot of factors, right? It was very much limited. There are limitations of classical physics. Lots of limitations on classical physics now. Remember that classical physics, I told you that classical physics, they dealt with bigger objects, or made us understand bigger objects. But one of their limitations was that while classical physics explained larger objects, it doesn't explain smaller objects. Right? So the first limitation is that classical physics breaks down when talking about smaller objects, right? Classical physics only explained big objects. It did not explain smaller objects, right? Smaller objects, by smaller objects, I mean like smaller objects like atoms, subatomic particles, right? Atoms and subatomic particles, the one we learned in physics. An atom, remember, an atom is the smallest particle of an element. When we started studying smaller things in the universe, classical physics was limited, because the only thing classical physics was able to tell us was bigger objects and not smaller objects. Now, the second limitation of classical physics was even though it described the speed of an object, it did not describe it only described when an object is moving at a pace that is not fast, right? But the moment an object starts becoming or starts going faster, or starts traveling at a speed that we call the speed of light, right? The speed of light, which we consider to be one of the highest speeds. When physics started studying how fast things go, classical physics was limited. Classical physics did not give us basic ideas like the speed of light. It didn't explain the speed of light, right? It was Albert Einstein in the 20th century that took us into this world of modern physics, where we were able to know things like the values of the speed of light, right, which is 3 exponent 8 meter per seconds square. Right? It was in modern physics that we had to learn things like the value of the speed of light, right? And how fast the speed of light is. We knew the value. We were able to measure it in modern physics, but classical physics did not give us that opportunity, right? So the second limitation of classical physics is that it breaks down when dealing with objects moving at the speed of light. So when we start dealing with objects moving at the speed of light, classical physics did not do us justice. That is where we now had to introduce something called relativity in physics. Right? Relativity is what gave us an idea of, how an object can move, at very high speeds, right? Relative to an observer, right? So it classical physics didn't tell us anything about it. So classical physics breaks down or is limited when an object starts getting smaller and smaller, and when things start moving faster and faster, right? It breaks down. Now, another limitation of classical physics was that it told us that time is absolute, right? Classical physics told us that time is absolute, but in modern physics, by absolute I mean time is fixed, right? So if two things are happening at the same time, with two people doing those two things at the same time, classical physics tells us that if person A and person B is doing something, the time that person A and person B are using to do that thing, as long as they began at the same time, the time they see the same time, right? They use the same time, right? The time in that instant is absolute, right? But when we progressed into modern physics, we saw that time is not absolute. Time is not fixed, and that if you have two observers looking at a time frame, that observer A will be seeing something different or having a different time than observer B, right? Which means time is relative to the observer, right? So the third limitation of classical physics was time not being absolute. But being relative, right? So if we have two people looking at the same thing or looking at an action at the same time, the time that the first person sees is not the time that the second person sees. Time in that instant is relative to the observers. The observers are the two people in the situation, right? So the first observer is seeing a different thing, the second observer is seeing a different thing, right? So their reference frame, right? Their reference frame is different, right? For instance, if supposing we're two persons, right? Let's say the first person is in a moving car and the second person is outside the car looking at a clock in the car. For instance, if person A, which is the person inside the car, the person is standing at a spot inside the car observing a clock inside that car, it will not be the same as the person outside the car observing the same clock, right? If the both of them will be having different time frames when they look at the clock, right? The person for the person inside the car, time is moving faster relative to him being the observer. for the person outside the car, time is not necessarily moving faster. Time may not necessarily be moving faster, right? It may not necessarily be moving faster. Time might be moving slower for the person in the car, right? So just to recap, right? Classical physics is a branch of physics that deals with macroscopic objects, right? Do not forget macroscopic objects, meaning big objects, not small objects. Secondly, we learned that, that objects do not fall at the same time. Two objects of different weights cannot fall at the same time when there's air resistance. But when there's no air resistance, assuming there's no air resistance, two objects of different weights can fall at the same time. It is possible for two objects of the same weight to fall at the same time. Right? That's the first observation. The second observation, the third thing we learned was the Aristotelian view that argued that the heavier objects will fall faster than the lighter objects without putting into consideration things like air resistance and gravity, of which I told you that Newton disproved, by proving that the heavier objects is only able to fall faster when there's air resistance, but when there's no air resistance, they fall at the same time, right? These were some of the things that we explained in today's class. This is my first class. The first time is not always going to be the best time, but with time we'll keep improving, studying. I hope you go back after this class. I'll be sending you a note. Go back and work on your classical physics knowledge. Learn about the law of falling bodies. Learn about things like projectile motion and inertia. Right, inertia. The next class today, the major emphasis today will be on the major emphasis today was on the law of falling bodies, which I told you Galileo did an experiment in an inclined plane in the Tower of Pisa, where in the presence of no air, heavier and lighter objects fell at the same time. It was the major emphasis on today's class. The next class will be on inertia, something called inertia. In the next class, we'll be dealing on inertia and projectile motion. Thank you very much. Have a nice day.